Okay, morning students. Is the sound clear? Please raise your hand. Okay, thank you. So we start, All right, okay. So for this chapter 6, all right, so it's just a very small topics. Okay, small chapters only. We have two subtopics only: radioactive decay and nuclear energy. All right, so if we look at the O syllabus, all right, which is the last chapter, chapter 5. So this part is removed from your syllabus because this part actually is your chemistry basics, which is that from chemistry you learn about proton number, nucleon number, isotopes, okay, and then the element X, the nuclide notations, how we write in the chemical symbol. All this you should know on your chemistry. So that's why there's introductions for the nucleus of an atom is have been removed there, but actually it's just your chemistry. Okay, just your chemistry basics. Sorry, so I hope that the sound is clear. Actually, today I'm not really feeling well, so see how first. Okay, if I really cannot, then I will finish class earlier a bit. Okay, so with the new syllabus, okay, this one later I will give you a handout. So I think by next week. Okay, for the radioactive decay, okay, we straight go to radioactive decay. So at first that I think you still need to know what is meant by the radioactive, right? If you look at the textbook here, so I hope that the textbook is with you. Okay, so the radioactive decay, if you look at the textbook here, got the info gallery. Radioactive decay actually is a randoms and spontaneous, okay, because it's not influenced by the temperature, pressure, and other physical factors, right? So means what I'm meaning here is radioactive decay is a process for the unstable nucleus. Okay, it's a process with an unstable nucleus means there's a radioactive lah. Radioactive, there's a one we call it unstable nucleus, right? When the nucleus is not stable, then it will emitting radioactive radiations, right? So that is what we call radioactive decay, right? Radioactive is referring to unstable nucleus. So the process to make it stable or more stable, so you are emitting radioactive radiations. Okay, and this is a radioactivity. This is a radioactivity. So in this process, okay, it will emit 3 different types of radioactive radiation, which is we have an alpha particles, beta particles, and the gamma ray. So these are 3 different types of radioactive radiations. And in this process, to emitting these 3 different types of radioactive radiations, this process actually is a random and spontaneous. Random means that we are unable to know actually what will emit. So far for the up to now, based on that the result study or in the lab or the practically, so they already concluded that it is a main 3 different type of radiations. Okay. So and then after that, the process is a spontaneous. Spontaneous means that we are unable to know when is it. Okay, because when you want to emit, it's just emit. You want to happen, it's just happen. Or we will say that when the radioactive want to decay, it's just decay. So it doesn't affect us by the temperature, pressure, or any other physical factor. It's not like the example, if you want to make the water boiling, we just need to make sure the temperature reach 100 degrees Celsius. When the moment temperature is 100 degrees Celsius at the atmospheric pressure 1 atm, then the water will boiling. So this is under control, under physical control, which is we know that how we're going to make the water boiling. But for this radioactive decay, we are unable to control it. We just only try to make it stable, or we try to keep it safety. We can try to keep it safety so that when it's decay, then we will avoid the leakage of that radioactive sources. Okay. So now your syllabus, the main focus is on the understanding about these three radiations, right? So there will be the basic equations for the each radiations here, which is this one is an alpha particle, we call alpha decay. So during this radioactive decay process, so the unstable nucleus it will emitting an alpha particle. This alpha particle we use 4,2 helium. Remember, 4,2 helium is the one presenting alpha particle, which is a positive 2. Positive 2. So that's why alpha particle in itself actually is positively charged. So in my module, I think I give you in the conclusion of tables here. So which is an alpha particles, we have the 4,2 heliums, and then the charge is positive 2 electric charge. Okay, and this is one we're going to use it in the balance equations. So in the old syllabus here, okay, all these things you still have to know okay, before I continue the alpha decay. All this radiation detector, actually you learn in your PT3 science. So you learn already what is the photographic frame, what is a Goldie spectroscope, okay, and then the diffusion trial chamber, okay. So the GM tube is a device that we study the radioactivities, okay. So all these measuring instrument for the detect the radioactive decay. So it's already you already learned in your PT science. So please recall back about all these things. Okay. So as I mentioned, all these basics during exam it may ask also. Okay. And anyway, when for the new syllabus regarding the alpha decay, beta decay, and the gamma ray decay, so you no longer need to study about this. The effect in the electric field, effect in the magnetic field, and also there's a penetrating power, ionizing power. But I still give you in this table, okay, because I noticed that the question it seems like they will ask also, all right? And then in your textbook, just touch a little bit only. So that's why I put it into a table, right? So this one, they don't even receive. So today I just let you see, okay, because it's very simple only. Okay, so when you look at your textbook, okay, after decay, so from we call it the parent nucleus will become the local nucleus plus alpha particle. So one of the questions that will be asked during the exam is, you ask you balance equations. And this balance equation is not that complicated as a chemistry that you need to know what is the local nuclei, so what is producing, okay, so no need. Okay, it's just do the simple mathematical calculation. Which is when balance the equations, you just need to balance the nucleon number before and after the total must be equal. So it means that here you will have this 210 equal to 206 plus 4. Right, so this is about the nucleon number. 210 must equal to 206 plus 4. Okay, and the proton number also same. This is based on the nucleon number, right? Okay, so and then the proton number also the same. It must the 84 beginnings proton number it must equal to the 82 plus 2 as well. Okay, so this is the basics, means that the general equation, the nucleon number, okay, the nucleon number must be the A must equal to the A plus 4. Okay, and then the proton number must equal to the proton number, okay, plus 2. so that this will be emit one alpha particle. So which is a 4-2 helium. All right. It's a simple mathematical calculation. So when you look at the example equations here, alpha, okay, so this is a 1. All right, so it means that the total nuclei itself, photon number -2, okay, nucleon number -4, so they can use to emit one alpha particle. The example, so far I think example you don't need to memorize because there are so many other examples. So during the exam, we will just ask you to balance the equation. Okay, SEMS will go through the beta decay. Beta decay, so is negatively charged. Then the beta particle is a 0, -1 electron. 0, -1 electrons. Right, so to balance the equations, photon number have to be +1. Z equal to Z plus 1 here. This is 1. Z plus 1. Okay, so that you can emit and electrons. Okay, so this is a negatively charged. And then the gamma ray, it doesn't make any change on the nucleon number and proton number because the gamma ray, okay, is not the particle. So gamma ray is just a electromagnetic radiations, electromagnetic wave. So as you learned last year, under the electromagnetic spectrum, so gamma ray is one of the spectrum which is the highest frequency, the shortest wavelength. So it's just a wave energy. So it doesn't make change on the nucleon number and the proton number. Okay, and the way you answer the question, I think that chemistry teacher have told you about this. We have the proton number, we have the nucleon number, but we don't have the neutron number. We only have the number of neutron. Okay, so please be alert about use of the names. Just like we have the proton number. Proton number is a noun. It's talking about that numbers of protons contained in that atom. Right? So, and then in the symbol, we have the proton number. So I think that's more for you that you should know about this, how we use this the terms in explain given the questions, given the answer. Okay, so you look at the textbook here. So as mentioned, you see alpha particle is a helium nucleus which consists of 2 proton, 2 neutron. Okay, during an alpha decay, an unstable, this is very important, an unstable nucleus leads this alpha particle to become more stable, okay, for a new elements. Right. So during this alpha decay, so we have a decrease. Actually, we have a decrease of 2 proton and 2 neutron in the atom itself. Atom itself, for this radioactive, okay, it will decrease 2 proton and 2 neutron. Okay, so is that who raised their hand? Okay, when come to the beta decay, you see it mentioned here. Beta decay is a fast-moving electrons. Okay, so during beta decay, there is a neutron in unstable nucleus decompose into 1 proton and 1 electron. Right? So sometimes the question will be a bit tricky. It will focus on this part because from that you look at the nucleon and the proton number itself. Okay, you will notice that the nucleon number it remain unchanged. Still 1 1. But the proton number, okay, from 0 increase to 1. You should know that the nucleon number actually is the numbers of protons plus neutron. So when it remain unchanged, right? Remain unchanged, but the proton itself actually +1. So it means that here we're going to +1 and then the neutron will be -1. That's why you say that there is 1 neutron okay, is decomposed into one proton and one electron. So the electron is here. Electron -1, proton is 1. Right, so remember about this. So when the question asks, during the beta decay, what is the chance of neutron and chance of proton? So you have to know that the neutron is -1, proton is +1. Neutron -1, proton +1. There is a chance of proton and the neutron involved for one beta decay. Right? When it comes to alpha decay will be -2 proton and -2 neutron. So that the neutron number will be -4, proton number -2. So there is a decrease, right? For the any parents nucleus, okay, it will be decreased 2 proton and decreased 2 neutron for an alpha decay. Right. So there is a mathematics pass. I think now your new silver is going to focus more on this to balance the equations. Okay, and then for the gamma ray, as I mentioned, gamma ray is just a high frequency electromagnetic wave. Right, so during the gamma decay, an unstable nucleus will release excess energy, right, to become more stable. Right, so since you got more energy, so when you release, so after a certain periods of time, it will become more stable. Right, during this gamma decay. So you look at the symbol itself. Okay, and so all during this decay, especially the gamma decay, because we doesn't see any change in the daughter nuclei, so only the change the nucleus have less energy. So that's why we need to have the detector, because only detector will show us a reading, show us a result to let us know what is decay. Even the alpha and beta, actually, we also don't know because we can't see. Right, that's why we still need the detector to tell us. So, and then detector learns already in your PT3 science. So there's the equations. And remember, for the simple decay equation, this is new introduced in your syllabus. How are we going to write the simple decay equation? This is a normal decay equation on the left here. Just like your chemistry, how we write the equation to balance it, to show all the nucleon number and proton number in the equation itself is balanced. But for the simple way to show that decay equation is this one, we just put the arrow. In the arrow from the parent nucleus become the daughter nuclei. So on top, what is decay? Then we just write like that. Okay. So there's a simple decay equations. Okay. So all this decay or the relative decay, as well, you know, the process is random and spontaneous. So, but somehow during that decay, it will become, especially like the example for the alpha decay and the beta decay. So it will reduce in mass. It will reduce in mass because the nucleon number is changed. Okay, nucleon number is changed. So even that beta decay nucleon number is not changed, but because of the decrease of the neutron and increase of proton, somehow the mass still have a difference. I mean that the mass of the nuclei itself. Okay, so and the process to reduce the mass getting smaller and smaller, right? So that this process is called half-life. Okay, half-life because all the derivative have a one's character, which is they have a certain constant time. Certain constant time, the mass it will decrease 50%. Right? Let's say example we're talking about the half-life of the one sample is 1 hour. It's 1 hour. 1 hour it will be from 1 kilogram to become half kilogram. So it will decrease the mass 50%. So, but this decrease 50% here is not linearly decrease. You cannot say, oh, this 1 hour, okay, it takes 1 hour to decrease 50%. So it means that half an hour will decrease 25%. No. You can't do that. It's only have a constant time to decrease 50%. And other than that, you cannot just use a simple linear ratio to know for reduce 25%, how long a time, to reduce 75%, how long time. No, you cannot just use a normal linear ratio. We have a special formula to do calculations on the cases like this. Okay, so okay, so this is the one. Half-life, the symbol is like this. It's given the textbook here. The symbol is like this. Make sure you know how to write this symbol. All right, so don't make it the symbol like writing like this. I don't want to see anyone like this in exam. This one is wrong. So it should be at the corner substrate here. So this one, okay, half-life. The time taken for the sample of the radioactive nuclide to decay to half of the initial number. This initial number, right, it can be referring to the mass. It can be referring to the radioactivities, which is the level of the radiations, especially for the gamma decay. Because gamma decay, there's no change of the mass. It's just releasing the energy. When releasing the energy, so especially when you use a GM tube to detect the radioactivities, it will show the number. Okay, so how high is the level of the activities? So all representing the numbers. So and the radioactivity detected, okay, from the initial number, okay, demand half of the original initial. Then the time taken, it will be the half-life. Okay, so here's the example, the series decay here. This series decay showing that uranium-238 decay until lead-206. All right, so the lead-206 is the stable. Once it reaches the lead-206, then it will become stable, then will be no longer decay anything. But the problem is from the uranium-238 decay until the final stable stage, right? In between, it will go through a series of the decay. There will be the decay that emit alpha, there will be decay emit beta, and so on. All right, so there's also gamma ray. Some it will take longer time, some it will take shorter time. Like this one for the uranium-238 become this one, the TS titanium. All right, so it's a 234. Emit an alpha particle, it will take 4.5 times 10 power 9 years for the original number to become 50%. So let's say we have a 100 gram uranium. So it will reduce to 50 gram uranium-238. Right? It will reduce to 50 gram uranium-238 by 4.5 times 10 power 9 years. Emit an alpha particle. So at the same time, okay, that alpha particle and then it will change to a local nuclide, this one. So when you write the equation, it will be like this lah. So it means that from the uranium-238, 92 here. So it will be go to alpha decay. So I write the simple decay equations for this 234. Okay, lithium 90. Okay. So after this one it will take 4.5 times 10 power 9 years. It doesn't mean that it will take this time, these durations, right? For the uranium totally become like this. No, don't be misunderstanding. It's just only for that uranium to decrease 50% of the original mass. Let's say original have 100 gram. After this year, after the 4.5 times 10 power 9 years, I still have 50 gram. I still have a 50 gram of uranium 238. Okay, and then it will continue. So in the process of an alpha decay, it will turn into this. And this, how much the mass? Depends lah. Right, how much the mass that we have? So based on that, okay, the atomic mass number that from here, then we're able to know how much the mass. Okay, so then after that, it will be take another 24.1 days for this one. Let's say, okay, let's say this become 50 grams already. So let's say, actually I don't know how much the mass here. Okay, it's not totally become 50 grams. So because some is released as alpha particle. Alpha particle also have the mass. Okay, and then at the same time also releasing the energy. So let's say we have a 30 gram as an example. Okay, let's say this 30 gram. This 30 gram will take another 24.1 day is to distinguish to the 15 gram for 24.1 day. All right. So reduce in mass, and then you get to this one. So it can see, so from here you can see it's so complicated for this radioactive decay actually. Right. So but as a beginning, we note in your limitations of syllabus, we don't go through the deep dive. Right, we just show you the series. I just don't want you misunderstanding that, after the 4.5 times 10 power 9 years, then I'll have no more uranium, all turn as this one, the TS234. It's not like that. Okay, it's not like that, please. Okay. So every round they have a different. So means that after the 4.5 times 10 power 9 years, this balance 50% of the uranium, it will go through another process, another one circle here. Right, so another every single half-life, it will be go through another circle. All right, so it will be quite complicated to study about this. Okay, so yeah, so that's why you see here the explanation given here. Uranium-238 is a radioactive element with a long half-life. Okay, so it's about 5,000 million years. This element will be trapped during the formations of rock. Okay, so the trapped uranium-238 will be decayed and eventually from the stable to form a stable date 206 as shown in the figure here. Okay, so the figure 6.6, right? So and in the rock, just the edge of rock can be estimated. Okay, the higher ratio, the older the rock. Okay, so this is the one. As I told you, original, let's say this rock contains 100%. 100% of the uranium. Okay, they got no any others. Okay, example, 100% of uranium. So after a certain periods of years, we don't know, but we get this lot sample. So let's say that the sample here showing that uranium only contains of 10%, 10%, and then the lead 206, okay, we have 90%. So we can do the calculations. How long of this? How much the edge of this rock? Okay, so means the original is 100%. Then now we only have 10%. So in that case, so you can go through process 50%. So another case will be 25%, and another will be 12.5%. So it means that we only have 10% here. We can estimate that it's more than the 3 half-life plus. Okay, because 4 half-life will be left only 6.25% after 4 half-life. After 4 half-life, the uranium will be only left 6.25%. But now I give you an example is this uranium contains of 10% compared to the lead that we have, the lead 206. So we can estimate this one is about 3 plus half-life. Okay. So to get exactly what is that estimate the edge will not only mention that 3 plus half-life. So we want to know exactly how many half-life, we can do the calculations. So there's a calculations. Okay, so then I will proceed to discuss about this. So just introduce about half-life so that you can have a little bit idea. And now I want to go back about this decay. Okay, you're going to learn how to determine valence equation to determine how many alpha, how many beta is decay for an sample. So example, look at these questions. Try to solve for me. Okay, we start with the simplest one first. Okay, so let's say I have the element, okay, element X lah, element X. So I simply put the numbers only. Okay, I simply put numbers only, element X. So let's say element X is 296, the nuclear number, and then the proton number, let's say, is 88. Okay, so after the one radiative decay, so it becomes element Y. So the local element nuclei is Y. So and okay, let's say this is two 288, and here is 86. Okay, so I want to know how many alpha, how many beta is decay. So find M and N. So I want to know how many alpha is decay, how many beta is decay. You have to write the equations and solve it like the way you learn from the mathematics, simultaneous equation. So once you have the answer already, okay, so show your answer in the message box. So anyone have the answer already? Attendance 60, all of 91, 60%, 66% attendance. Okay, yeah. So with the others one, good luck lah, huh? Hi, come. Anyone give me the answer? You need to form equations for the nucleon number and the equations of the proton number. Then after that, you solve it by simultaneous equations. So you will get the answer for the M and the N. Why still no one share the answer? Come on. Just like I told you already, alpha particle is what? Alpha particle is a 4,2 helium. Alpha particle is a 4,2 helium. And the beta particle is 0, -1 electrons. Okay, thank you for the sharing the answer. All right, I think the answer is correct. So for those still not really sure how to get the answer correctly, all right. Okay, as I mentioned, form the equation first, right? Which is on the nucleon number. So the parent nucleus that you have here is a 296. This one, your nucleon number, and then it should be equal to your the daughter nuclei here is a 288 plus what? Plus this. This one is a 4,2 helium, right? So 4,2 helium, but you don't know how many helium, how many alpha particles you have. You have the M here. So M multiply this one, it becomes the 4M. And this one is a 0, -1 electron. So N multiply 0, nothing. Right? So it's just only 4N. Then from here, actually, you solve the problems already. Then you will get the M will be equal to the 296 minus 288 divided by 4. So we'll get the M equal to 2. So that's why we know there is a 2 helium. And the proton number, look at here. Proton number, we have the 88 beginnings. It should be equal to 86 plus what? Plus 2M. Plus 2M. Okay, helium proton number is 2. And the numbers of helium is M. So that's why we have the 2M here. But the M, we already know M is 2. Right? So, and then plus what? Plus this one, N multiply -1. So it's the N multiply -1 here. Then end up, so here is equal to 4. That means that you have the, okay, this one. So means that you have the 88 equal to 90 minus N. So your N will equal to 90 minus 88. That's why you have N equal to 2. So now you have the 2 alpha and 2 beta. So the answer is M equal to 2, N equal to 2. This is how we solve by writing the equations. If there's a paper 2, make sure you're able to know how to write equation to show the correct answer. Is this okay? Yes, please raise your hand. Okay, so now we try the other formats of question. So the question it may give you in the graph, all right? So when give you in the graph, please be alert, lah. What kind of graph you give, right? So now look at these questions. So I give you, this is a number of neutron, and this is a proton number. Okay, so example. So let's say here is examples only. The number I just simply put. Okay, so let's say here is 98, and this one let's say is okay, 48. Okay. Okay, so this is for the element P example. Element P. So here 96. This one let me do some calculation first now. Okay, so this one, sorry. Okay, this is 95. Here 47. This is the element Q. And afterwards, another ones. Here is the 90. 91. Okay, 91s. And this is 43. Elements out. Okay. So from the element P to Q, Q to R, right? So this is a series decay. This one is series decay. So it means that there's an element from the P decay into the Q and Q decay into R. So I want to know overall how many alpha and how many beta decay. So try it with me now. How many alpha, how many beta decay? Once you have the answer already, please share your answer. Anyone got the answer already? Please faster. Why student one should answer? Please faster.
Teacher, the N is the nucleon number, is it?
I just mentioned we got no such thing neutron number. We only have the numbers of neutron. Okay. If you want to have a neutron number, then you have to publish the paper to prove that you have found something they call neutron number. So far, now up to date now, people only count how many numbers of neutron, right? So you give a symbol n, there is an how many numbers of neutron. Right, so remember how you get your nucleon number. So you need to write equation one by one. For this question, you need to write equation one by one, which is you need to form the equation from the P decay to Q. What decay you get. And afterward, from the Q decay to R. How many alpha, how many beta you get. Okay, and then one more thing that as a reminder for you, when we write the equations, we only able to know how many alpha, how many beta decay. We are unable to know whether there is a gamma decay or not, because gamma is just a electromagnetic wave. So in the equation itself, it doesn't show any symptoms. Okay, because in the equation, we only see that the change of the nucleon number and the change of the proton number. This is only let us know about the proton. This only let us know about the alpha and beta decay. So only that we can do by calculations. Gamma, unless the question told you, then you will know. Or practically, we use a detector to check Okay, the radioactivities, the energy. So only we know whether there is a gamma decay or not, or there's some specific detector based on the characteristic of the gamma. Later we discuss. Only we may know whether there's gamma decay or not. Okay, so far in your current syllabus, they are more concerned about balance equation to know about alpha and beta actually. So got the answers already?哎，黄婷婷啊，嘴巴晶晶。Can do or not? Or still doing? Cannot do, raise your hand. Okay, cosine 3 alpha 5 beta. So much so much beta. I also know very sure this is that much beta. Okay, so let me so let's do together. So I also not sure whether I'm give you correctly or wrong. Okay. So anyway, hopefully I don't calculate wrongly lah. Okay. So now we do together. Okay, first PQR. So P, what is your nucleon number? How much is the nucleon number of P? Nucleon number of P is 146. Proton number of P, 48. Okay, and then the nucleon numbers of Q, 142. Proton number of Q, 47. Okay, and nucleon numbers of R, okay, proton number of R, 43. This is what you have before you do. Then for you're going to do 146, 48, element P. Right? Due to the radiative decay, it becomes 142, Q, 47. So here you got, okay, you don't know how many, let's say we put any symbol here lah. So let's say I put the M for the alpha, N for beta. Okay, so next I will have a 142, 47 element Q, and 143, 43 element R. Okay. Okay. So this will another, okay, so let's put another symbol lah. Let's say it's a K alpha. What arrow here? Plus K alpha plus L beta. Example. Okay, so we solve it one by one. First one, you should have 146 equal to 142 plus 4m plus 0n. Okay, and 48. So here you will get m equal to, okay, m will equal to 1. This one m will equal to 1. Okay, and 48 will equal to 47 plus 47 plus 2 multiply 1 minus n. Okay, so here will be the 49. So from here, so n will equal to 1. All right, so means that now we have a 1 alpha, 1 beta. Okay, and then the next 142 equal to 134 plus 4k. Okay, then here k will equal to 2. Right, k will equal to 2, and we have 47s equal to 43 plus 2k minus L. Okay, so k equal to 2, then we have a 4. So from here, L equal to 0. Then we have a 2, 0. So end up total, we have the 1 plus 2 alpha and 1 plus 0 beta. So we have the 3 alpha, 1 beta. X is 3. Okay, what x alpha, x beta. Okay, y beta, sorry. Okay, so x equal to m plus k, so it's equal to 3. Y equal to the n plus L, so it's a 1 plus 0, so only 1. 3 alpha, 1 beta. Understand or not? If yes, please raise your hand. So basically, that is mathematical equations only. It's just like you learn the simultaneous equation. Okay, just be careful about here stuff. So this one, if we give you here is A, is a nucleon number, then you no need to write the total the nucleon number by neutron plus proton. All right, but this one, because it gives you a neutron, then you have to find what is the nucleon number by the neutron plus proton. Okay, so be alert about this lah. And when you change it into the nucleon number, the graph, it may go back. Example, if you change into the nucleon number, so let's say here's a nucleon number now, A, and then proton number Z. So here, let's say I give you the 190. So that is element P. Okay, still again, another one, element P, we don't know. So let's say here is 80. Right. So, and so this will be 100, let's say 182. And then 82. So here become 82. This is Q. And after that, I have this, let's say 170. And 78 here. So this is an element R. Okay, so from P to Q, Q to R. P to Q, Q to R. All right, again. So P to Q, Q to R. So how many alpha? How many beta? So got the answers already. Oh, you. Phi alpha, 10 beta. Any others got the same answer or different answer? All agree with this answer? All right, so have a look here. So element P, what we have a 190, proton number 80. Element Q, what you have 182, right? Proton number 82. So when you look at the nucleon number, so you already know that is minus S. Minus S means it must be the 2 alpha. So for 2 heliums here, it is. So here we know already. Right, so that only with that you balance your nucleon number. Then plus how many alpha here? So 82 plus 2, 84. 84 to make it become 80, so we must 4, 0, -1 electron. So we must have 4 electrons here. Then only you can balance the equations. All right, so to get 2 or 4, you can follow the step from the equation that I told you just now, use a symbol. All right, or you want to balance it like this, up to you lah. Okay, so the next 182, 82Q to R 78, and how much we have here? 170, 170. So 82, 170, so it means that it's minus 12. Minus 12 must be based on the 3 helium. So 4, 3 is 12. So 3 helium, then 2. So 3, 2 is 6. 6 plus 78. 6 plus 78, we got the 84, but the original 82 only, so it means that you have the minus 2. You have to plus minus 2. So -1, 2, -1 electron. So is that balanced? 3, 2, 6, 6, 78 plus 6, 84. 84 minus 2, 82. Oh, all right. So actually, how many proton we have? We have a 2, 3. So we have to find alpha. We have to find alpha, and we have 4, 2. We only have 6 beta. That is how you get 10 beta. Where is your mistake? So total we have the 6 beta.
The proton don't need the proton below don't need minus.
Which one?
Like the helium there, like 224, then 80 minus 4, that don't need.
80 minus 4. It means that from P to Q or what?
Yeah, P to Q.
P to Q. Let me see. P to Q, you have 80 equal to 82 or I left one here. Oh, okay. Sorry, it's my mistake. All right, so I mix up here. So it's a 2 multiplied 2. So 2, 2, 4, 82. So altogether 86 here. Yeah. So you're right. So here to make 60, you have to 6. Yeah, 6, right? 6 beta, is it?
Yeah.
6 beta. Okay, so altogether still 8 beta. No, 10 beta.
No, the up there is 8, right?
Which one?
The 6, not 6 is 8 one.
Which one? 80?
The
2, 2, 4, right?
2, 8. I count now is 8 for the second one.
For second one,
Equation second.
okay, equation second. So 82 to 78, right? Equal 78 plus 326. 326 plus this one 80, how much? 84, is it? 84. So just only minus 2.
No, teacher, the first equation 92 minus 4 minus 6, not 80 what?
92.
92 minus 4 minus 8 equals to 80. So it's 10 beta, yeah.
Element, this one's 82, no 92.
Oh, that's right. Okay, okay.
So sorry for my handwriting. Sorry.
I say to 92, sorry, teacher.
This is 82. If the 92, then the next equation, so I think you will get 92, 70, 84, 6. Then you will even, you cannot balance equations.
Teacher, for me, I counted because for the P to Q, the helium is 2 times 2 equals to 4. So I minus out first. So it's like 80 equals to 76 plus 4. Then if 1 electron, 76 to 82 will be 6 electrons. So 6 beta for the first one. Like
6
that.
beta, correct, right?
Yeah.
Then the second one, 2 beta only, right?
The second one, because it's 3 helium, so 3 times 2 is 6. So 82 minus 6 is 76.
Okay.
Oh, okay, teacher, sorry, am I wrong?
So it's a 2 beta only, right? The second.
Yeah.
So altogether is 5 alpha, 8 beta, right? All right, so just be careful lah. So I also have count wrongly here. So it's better write equations lah. So you see when I don't write the simultaneous equation so you see do wrongly already. So don't follow my calendar mistake here lah. Just like follow from beginning, write the equations, simultaneous equation, do like this, it will be safer lah. So don't be go to shortcut lah. So go slowly, be safe, right? So make sure that get the correct answer. This is a question that you must make sure the score, because the calculation is a simple calculation. They got no complicated formula involved here, right? And nearly every year it will deserve a questions, at least one question for this, right? So, and then it will make this question like the primary school mathematics question. Do you know? It will write like this. It will give you a question like this. Example. It will just write, let's say uranium 238, 92, and then becomes one element here. Let's say the DH here. Then we'll write here 2, 3. Example, this one was 232. Example 230, and then here it will be right 90. Example. Then after that you put it here. You put here a box of alpha and a box of beta. So after you fill out the blank, all right? So, or you will give you another way now. You tell you how many alpha, and then you put the box here. Put the box here. Ask you to fill out the blank. So it's just like the primary school mathematics. Ask you to fill out the blank. Okay. So make sure this calculation is scored, huh? All right. So that is about the calculation involved for the CD decay. Okay, CD decay, just now we try for the CD decay, gamma decay, beta decay, and alpha decay. So this is how we do. Okay, so now we're talking about this half-right. Okay. So, okay, when half-right, right, we have this example for the activities. You can do it at home, right? Just a very simple one. Okay, you get the dice. Okay, and then after that, so in the back, you didn't need to take it out. So just follow a step. Number. So after that, you remove. You can simply put any number. Let's say when you want to withdraw, take out. You will take out the numbers of 2 for all the dice. Have number 2, you remove it, and then count how much the balance. Then we repeat it. So after you plot the graph, you'll notice that they will have the constant numbers of the constant number of throw. You throw all the dice, then you will notice there's a constant number. The numbers of dice remains. No matter how number you choose every time, you repeat the same experiment, you will notice that the number of dice remaining half is the same number of throw. Okay, so that is a concept about half-life. Actually, we're talking about the possibilities here. Okay, so and now the concept of half-life, without the formula, we will apply this. This one we call it timeline. Timeline about the formula, how we solve it by without the formula. The formula is here. This is formula. Later talking about this formula. This is the formula. Okay. So for that, if we apply the calculation by showing the timeline, okay, which is this one timeline. So it means that for the original 100%, and then after one half-life, so after one half-life here, it will left 50%. So it means that here, actually it decreased 50% already. Okay. Then later on, another half-life. So for the 50% original, it will decrease another 50%. So now you only left 25%. So in this case, you're going to minus 50% again. Minus 50% from the original. So you left 25. Then accumulated, you already decreased 75%. That's why you only left 25%. 75% is already decayed. Right? 75 decayed, so you only left 25% after two half-life. Okay, another half-life. Now you got 25% as the original. The original, this one, we're going to minus 2. Not minus 2, but divided 2, so you only left 12.5%. Then this is another half-life. So every time it will be decreased 50% of your previous initial number. Right? So this is about half-life. Okay. This timeline, the timeline like this is only allow us to solve the problems for the complete half-life. Right? So there is a one that you can see from the 150, 25, 12.5, and so on 6.25. You're only able to count how many complete half-life. So let's say I say that I want to know how many half-life if the sample that I have now is only left 30% of the original. If I only left 30% of its original, that's what I have. I only left 30%. So left 30%, 30% it should be somewhere here. Somewhere in between here, 30%. Because after two half-life, you only left 25%. But now you have sampled more than that. So it means that you haven't complete two half-life yet. Once you complete two half-life, you only left 25%. That's the concept. So when I say that I have 30% in hand, so how many half-life I have? Then this are question you cannot solve with timeline. You cannot based on ratio. Then only way to solve this kind of questions, you have to use formula. So the timeline only allow us to solve the question that have complete half-life. So let's say example, the table 6.2 here. Table 6.2 is showing there's a 5 half-life. So 5 half-life, original, you have an N0. After 5 half-life, you have the 31 divided by 32 N0. Okay. So number of the decayed radioactive nuclei. So you only have 1 over 32. You only have 1 over 32 in your hand. All right? And then 31 over 32 is already decayed. So this is for complete half-life. Okay, so if we have incomplete half-life, then we have the apply formula. So as I apply formula here, N in the formula is the number of radioactive that is no decay. No decay, as an example, I said that I have a 30% in hand. So this is still I have. So I already lost 70%. Original is 100%, no? Okay. So I want to know how many half-life. And then in this formula, the small n here is the numbers of half-life. So by the timeline, we estimate it should be 1 point something. Because it's 2 half-life, then we'll be left 25%. But we still have 30%. So it's estimate 1 point something half-life. So now try to apply this formula to let me know if you still have 30% in your hand, how many half-life actually you have. So calculate for me to find this n. That is your mathematics, MS, MS. 30% you left. So how many half-life? Any idea how to solve it? You have to use what calculations? Anyone know what calculation you have to use? Apply formula, find the power, the n is what? Oh. So when you substitute equations, what it will be? So use these equations. So you have 30% here. You can put 0.3 lah, huh? Okay, or you want to put 30, up to you lah. Right, 1% also can, never mind. So 30%, it should be equal to 1/2 power of n and multiply 100%. So it means that 1/2 power n is equal to 30% divided 100%. So equal to 0.3. So how to find the n? Now you have the 1/2 power of n is equal to 0.3. So how to determine n? Anyone got the answer? How much n? I already show you the substitution everything, and now you only do the final calculation to tell me the n. That is your MS. Come on. No one can get answer. Then how's your guys score MS? Hoàng Tinh Tinh Jing Jing Come on, girls. Are you still with me? All right, so yes, 1.37, 1.74. Okay, so for nowadays, you better give 3 decimal. I also don't know what they want. 3 decimal will be safer. All right, so if it's 3 decimal, your answer should be 1.737. Okay, 1.737 half-life. 1.737 half-life, so don't give 1.74 for safer. The answer like this, keep 3 decimal. Anyone cannot get this answer, please raise up your hand. You got no idea how to get this answer, raise up your hand. Oh no, So you have to use a log the animal to answer this. So means here, right? Okay, so you have and get 0.5 equal to 0.3. Okay, so the n will be equal to, you want to use a best 10 or in number log also can, no problems. Okay, it's the same answer. 0.3 become, okay, you have 0.4, so you have the answer 1.737. Okay, so that is about the calculation with the formulas. Okay, and you also need to learn how to study the decay curve graph. Which one have a lower decay rate? Which one have a higher decay rate? So we look at the half-life. If the half-life is shorter, means that you have a higher decay rate. So and vice versa, longer the half-life, so the lower the decay rate, because it take longer time to decay. So the rate of decay will be lower. Okay. And this is what I told you, the question I showed before in the last year SPM 2022. Okay. So which is the axis given here is wrong. Right? It's not providing the linear axis. If we follow that the axis given the question, the graph will become straight line, not the decay curve. Right, if you decay curve, if you follow the normal linear ratio of the scale. Normal linear ratio of the scale, not like the last year SPM, it gives you the multiply scale. Multiply scale is not a linear scale, which is that we seldom plot the graph like that. So I think the guys said the question is crazy. Okay. So to draft this decay curve, right? So there's a technique. We cannot just simply draw this decay curve. So now you can take a paper, try and learn together how we draft the decay curve. Right? So first one, you need to measure vertical line. Usually I advise students you measure 11 centimeter. 11 centimeter, draw a vertical line, y-axis 11 centimeter, and the x-axis doesn't matter, maybe or 10 or 8 centimeter. Okay. So that is an x-axis. And the y-axis here is your here is your nucleon number. So let's say put the n here. This one is a time. So time can have any units. Depends on whether there's a long half-life or short half-life. So as long as there's a time half-life. For the time axis here to determine the half-life. Okay, so when you draw this 11 centimeter, okay, from the bottom here 0, and then you measure 10 centimeter high, you mark 10 centimeter high, you mark here as an end knot. This one indicate for the beginning 100%. 10 centimeter. So after that, the next one you're going to decay 50%, only remain 50%, remain 50%. So you measure 5 centimeter, you mark. So there will be the N0 over 2. Here decay 50%. Now you only left 50%. So this one is the 50% left. So then after that, 5 centimeter now divided half. So another 2.5%, 2.5 centimeter. So 2.5 centimeter you mark here will be N0 over 4. N0 over 4. So there's a moment that you have left 25%. So this 2.5 centimeter, you divided half again. So 1.25 centimeter, 1.25 centimeter. So it will be N0 over 8. N0 over 8. Divided half again. So N0 over 8. Now you only have left 12.5%. So this is on the y-axis. So on the x-axis, you use your ruler, mark the constant division. Because the half-right is constant time. So maybe you mark every 2 centimeter, you mark. Every 2 centimeter, you mark. Every 2 centimeter, you mark. All right. So this is your 1 half-right. This is your 2 half-right. There is your 3rd half-right. Okay. So beginning, before you start decay, there is the original you have, beginning, time starting 0. And afterwards, after 1 half-life, here's a 1 half-life, you will be left N over 2. So that is after 1 half-life. And this is after 2 half-life. You have this after 2 half-life. After 3 half-life, then you have here after 3 half-life. So based on this, then you will get your decay curve. So you draw the smooth decay curve. Right? The more half-life you can show, they will be more accurate. Okay. So don't use the ruler draw a straight line. You can't get a straight line. This is the decay curve. Right? So this is how we draft our decay curve. Just like this. Okay, so as an example given here. All right. Okay, so when you have another one which is a shorter half-life, so you will see that's a different decay rate. That's all. Okay, so the example 1 and the example 2, okay, is the one that I told you just now. When you have the complete half-life, you no need to use formula, and you can easily solve. Even for a question like this, this question is using the formula, right? And now you get the number of half-life is 5. So actually, we still can try to use a timeline to solve the problem, right? It not necessarily must apply formula. Like this one you see, a sample of a radioactive material stored in the laboratory has an initial activity. So initial activity 480 counts per second. 480 counts per second. So if it's half-life is 6 minutes. So how much activity after 30 minutes? So after time 30 minutes, so 30 divided by 1 half-life, 6 minutes. So it means that you have a 5 half-life. So the 5 half-life. So if you want to write the equation, it's like this actually. Actually like this. If you want the equation, so n half-life is equal to 30 minutes. We don't know how many half-life, but the time taken is 30 minutes. 30 minutes. So, and then the n will equal to 30 divided by half-life. So half-life is 6. So 30 divided 6. So equal to 5. So 5 numbers of half-life. Then for starting is a 480 per second. 1 half-life, so 240. Another half-life, 120. Another half-life, 60. Another half-life, 30. 1, 2, 3, 4 half-life. So 5 half-life, 15. So the answer will be 15 per second. you still can use a timeline to solve the problem. So the answer is 15 per second. Not necessarily must apply formula. But if you want to use half-life, the timeline to solve the problem, make sure it's a complete half-life. If the half-life, let's say 4.8, 4.7, so you have no choice. Because it's not the integer, no number, so you have to apply formula. Then only you can get the answer. Okay. So here are the textbook give you the 3 examples about the half-life. So I think the calculation is quite simple and easy. All right, so I think that's all for our 6.1. Okay. So far, is this okay? So this morning we only focus on the half-life and the radioactive decay. So if okay, raise our hand, then our class will be just finished here. All right, so the next class we will continue with the 6.2 about the nuclear energy. So that one I think will be take another 1.5 hours. Okay, we will finish our this chapter. Okay, so anyway, if you look at the calendars here, so next week I was still around in the school, but after that, 24th to 27th will be roll around. So because we and Lucian eating, we will go to the Malacca for the carnival stamp Bangsaan, and after that 28th will be the public holiday, and first and second I think so. First and second, I think affected is Francis and Charles lah. Okay, on the Sunday class. So I won't be around first and second. I will take leave. I'm sending my son go to Sabah for the registrations of his university. Then only I come back on 3rd. Okay. So after that, your exam will be begins on the 22nd. So we still have 2 more weeks to finish our syllabus of the chapter 5. Okay, chapter 5 in the school. I think shouldn't be a problem for us to complete the syllabus lah. Plus the extra class still remains on the Saturday. I will inform you. Okay, so for next week so far I think it's normal. For the extra online class. Okay, to finish our chapter 6 and chapter 7. Chapter 7 I think I will use the online to finish it also. Means basically based on the current plan like this, our trial will be complete cover the whole syllabus for our trial. So you may start to prepare from now. Okay, so at first I thought a trial will be not included all the chapter, but I think we can complete the syllabus. Okay, yes. Amani before 22nd or ruling that week. Okay, timetable haven't out yet, but if you follow the mid-year style, I think the Amari will be they will arrange by the end of the exams lah. So that day we having the same day with the accounts, right? So I think so that will be the last day. I think by the end of the trials lah. I think not going to before 22nd lah. Okay, everything will start 22nd onward. Okay. So anything else that you concerned? Okay, no, huh? So that's all. Okay, thank you for joining class. Okay, that's all for this morning. Thank you.
Thank you, teacher.
Teacher.
Bye.
Thank you, teacher.